Okay, so can you hear me? All right, so if you recall, in our last lecture, we talked about convergence in law, convergence in probability, convergence almost surely, and convergence in the arithmetic. And we said that almost sure convergence implies convergence in probability. Convergence in the arithmetic also implies convergence in probability. And convergence in probability implies convergence in law. And we give you some important partial converses. So one exception, important exception is that if xn converges in law to a constant instead of a random variable, then we would have convergence in probability. This is the first important exception. And we also talk about when you have almost sure convergence, under what regularity conditions can you have convergence in the arith mean? So you go, how can you go from here to here? You need to really control the expectation of the random sequencing somehow. Okay, and another result we talked about but didn't finish is this. When you have convergence in probability, although you cannot have convergence almost surely, but you will be able to find a subsequence such that the subsequence converges in almost surely. Okay, so we're going to prove that today. So this is equivalent to for any subsequence, I call it X and J, and J from 1 to infinity, there exists a subsequence, which is a subsequence of this. We call that X and J, J from 1 to infinity, such that X and J converges almost surely to X. So this is what we talked about but didn't prove last time. And I said to prove this, we will use the famous Borel-Cantelli lemma so that we can go from the left-hand side to the right-hand side. But this is an equivalence. So from right to left, it's actually pretty easy. We can just do a counter proof. So we will do that first. Go from right to left. So when we want to do a counter proof, we just assume this doesn't hold. So if xn does not converge in probability to x, then we are able to show that this cannot hold, right? Then we prove this direction. All right, so how can we say that? We're going to use the definition of convergence in probability. So what is that? So remember, we have the convergence in probability using the epsilon delta definition. Is equivalent to, this is defined as for any delta positive. Recall this delta is what we use to denote the violation probability, and epsilon greater than 0. This epsilon is for that neighborhood size. Then we would have an n. There would exist an n depending on delta and e, such that we would have, sorry, I should say n0, such that we would have the probability that xn minus x greater than epsilon, this event will be under the violation probability delta for all n greater than n0, right? So if we have this, we have the definition of convergence in probability. But now we're saying we don't have convergence in probability. Then what's the converse of this? How do we reverse this argument? Then it will be that this is for any epsilon delta. Then the reverse of this would be there exists some delta and some epsilon, right? so that we don't have this event. All right, so basically, I'm going to write it down. When we say it doesn't converge, then it means that there exists a violation case, certain delta greater than 0 and epsilon greater than 0, such that we would have the probability that xn minus x greater than epsilon, this probability would be greater or equal than delta for infinitely many n. Okay, so this will be the violation because we can never find an n0 such that after that n0, these probabilities will be under delta. So that implies we can find infinitely many n with this violation. Does that make sense? Okay, so with this, then we can pick those n and call them as a subsequence nj. So given this delta, given this epsilon, we find all the n's such that this probability is greater or equal than delta, and we call them nj. So then you see, and this you can see because it's infinitely many, this j can go from 1 to infinity. Then with this subsequence, clearly you see they cannot converge almost surely, right? So basically, this subsequence, hence, this subsequence x and j, by this violation, it will not converge to improbability to x, right? And therefore, because we know almost sure convergence is stronger than convergence in probability, then they cannot converge almost surely to x. Then violation, right? Because we are saying that for any subsequence, we can always find a subsequence that converge almost surely, but this doesn't converge almost surely. Therefore, we cannot pick a subsequence that converge almost surely. Does that make sense to everyone? So this is the counterproof just to show that when you satisfy this, we must have convergence in probability. Otherwise, if we don't have convergence in probability, then we can find a way to pick a subsequence, and the subsequence will not converge almost surely to a limit, to the random variable limit. Okay, so that's it. And this is the one direction. How about the other direction? And that's the more difficult one, to go from convergence almost surely, convergence and probability to the subsequence. Okay, so we will just prove this by saying that given the left, we are able to find a subsequence that converges almost surely to x. But because this is actually general, and it implies that if we don't start from the whole sequence, but starting from a subsequence, we can still find a subsequence that converges almost surely to x. So it's actually implied. The reason is just because if this xn converges if this xn converges in probability to x, then it's any subsequence also converges in probability to x. So therefore, we can say there exists a subsequence, and that's just a more general way of saying this. But we're just going to prove that given x, to prove that xn converges in probability to x means that we can pick a subsequence nj such that x and j converges almost surely to x. We just need to prove this so that this will also hold. All right, how do we do it? So this will rely on the Borel-Cantelli lemma. So let me just give the statement we need for this proof. And we just need the first statement. So it has two lemmas, and I'm just going to give you the lemma 1. So what this says is that if we have a sequence of events, if the sum of the probability of the events, j go from 1 to infinity, is finite, then we would have this conclusion. That is, the probability that aj happens infinitely often has probability 0, which means that we cannot have infinitely many events happen. How can we express that infinitely often, or short as I dot O dot, in using the set operations? In fact, it is actually this. This can be written equivalently as the limit of the probability with the union. We say j go from n to infinity, aj, and we let n goes to infinity. That's it. So you see what this means is that, say I have my set order A1, A2, A3, AN, and so on. So what I'm doing here is that I'm taking the union for all the sets afterwards, and here and here. So I'm getting the union, and I'm pushing the left boundary to infinity. So essentially, you see, I'm getting to the later and later events together and see if any of the later events happen. That's what the union means, because if one of them happens, then the union happens, right? So therefore, I'm saying that by pushing n, the left boundary, to the limit, I'm just saying that no matter how late I go to my order, I can always find an event that would happen. That's infinitely often. So essentially, this is a very strong result. It says that as long as you can know the probability of each set, and you can do the summation and let the summation go to the infinity, right? So the j goes to infinity. And then if this is finite, then you can say for sure that I don't have infinitely often sets that happen, events that happen. So what it means is that you can always find somewhere in your sequence of events, after that, you will not have any events that happen. So there are only finite of them that happen. Okay, does this make sense to you? The Borel-Cantelli lemma alone. So we just can go from the sum of probabilities to this probability of infinitely often. That's what we want. And why is that? The reason is because we need this infinitely often probability for our definition of almost surely. That's why. So if you recall, what's the almost sure convergence definition again? If you recall the definition 2, okay. If we want to show x and j converges almost surely to x, what definition do we need? The alternative definition, or we say definition 2 of this almost sure convergence, is that for any epsilon greater than 0, we would have the probability, or I may say this n goes to infinity, the probability that, let me see if I can say this, yeah. The event that, okay, so xj minus x and j minus x greater than epsilon. This event happens infinitely often. This needs to have a limit 0. So you see, what this means is that given any epsilon greater than 0, I will not have infinitely many of x and j that's not in the epsilon neighborhood of x, right? You recall what we have in the definition is that given the epsilon, we can always find an n here so that for all the nj greater than n, they are x and j's are within the epsilon neighborhood of x. We have that definition. So here we are just telling you the reverse, right? So we don't have infinitely x and j that violate this neighborhood requirement, right? So that's what we need. And you see how this looks like this Borel-Cantelli lemma 1's conclusion. So this is saying that, this probability can be written as the probability that this x and j minus x greater than epsilon infinitely often is with probability 0. That's it. So don't think too much about the infinitely often. It's just a shorter way of writing this limit. But if you prefer this limit, you can write it, right? That's more exact. Okay, so you see, since this is what we want to prove, what this Borel-Cantelli lemma tells us, we just need to do the calculation of the probability of x and j minus x, absolute difference greater than epsilon. We just need to know that probability for the x and j's. And we just need to show that the sum of their probabilities is finite, and we're fine. Okay, and how can we pick, because we are allowed to pick a subsequence nj. Nj's are our own choice. How can we pick the nj's? We just need to pick the nj's such that pick the nj such that the sum j from 1 to infinity probability x and j minus x greater than epsilon, okay, is finite. That's it. Okay. So does it make sense so far? Okay, so how can we pick it? Any idea from the audience? We're almost there. Yes. Exactly. Yeah, that's right. That's the exactly correct answer. Yeah, so we just pick, so we just, and the answer is that we pick nj such that we can just do this. The probability, we can actually say, the nj. I'm just giving one example. Greater than epsilon is, let me just give you one simple example so you can see it. So let's say we just pick it as 1 over j squared. Then we know because the summation j from 1 to infinity 1 over j squared is finite, right? So this is a well-known result. Then we're fine. So this is just one example. You don't have to pick 1 over j squared. You have other choices. But the goal is that when you pick the subsequence, you make sure that this violation probability together, the sum will be finite, and you're done. So yeah, so you see with the Borel-Cantelli lemma, this result is quite straightforward. And we rely on this important result to go from the sum of probabilities to the probability of an infinitely often or infinitely many events that happen. So I hope this can give you some idea to see, yeah, So this is the definition of convergence almost surely. And this can again show you the difference between convergence almost surely and convergence in probability alone. So you see, again, for the convergence in probability alone, we look at this event just for the n, but not for everything after the n. While for the almost sure convergence, as I said in the beginning, we care about each realization. So you don't only look at n, you look at all the random variables in that realization after the n. So therefore, it is infinitely often. So you need this to be, sorry, I should say, you need this xn to be within the epsilon neighborhood with infinitely often, not just the xn is within. Okay, so, and also I remember after the class last time, so I think it's the student sitting on the right. So I think you made a very nice comment when you talked to me. So you said that how can we interpret this result, right? You said that basically when we consider the convergence in probability, but not convergence almost surely, we actually have the case, as we gave in the counter example, it's that every realization not convergent, but we have on average, it's convergent, right? And you said that the reason we can have this almost sure convergence for subsequence is because we can rule out those exceptions. And those exceptions are just, we can rule them out. And then these are finite. And for an infinite subsequence, we can have the convergence almost surely, right? I think that intuition itself is very good. Yeah. Yeah. And the reason is just for simplicity. So as I said, because we have the convergence in probability for the whole sequence, so we will still have the convergence in probability for any subsequence. Well, so basically you can think about, let me say, so we can think about, so what I gave the proof is that, so maybe I should say more explicitly. So what we prove here is that if we have x and j convergent probability to x, then there exists a subsequence x and j such that x and j converges almost surely to x. Right, so that's what we actually, that proof can be applied to here. Okay. All right, so that's all I want to say about the 4 modes of convergence. Do we have any questions for this part? And more details are in the lecture notes. So if you want to read carefully, you will have time to read the notes. And also I want to say that, yeah, the counter examples are always helpful for you to concretize what we say here using the notations. Okay, so that's it. So today, the second topic, or next topic, I shouldn't say second topic. Next topic, we will focus on the convergence in law. So we'll talk about how the foundations of the convergence in law and what we can use to prove convergence in law, because that's what we use the most for our asymptotics. When we have a statistics, we want to know its distribution when the sample size is large. Okay, so convergence in law. So the fundamental result we are going to show is what we call the Lévy's continuity theorem. So this is the most important result we are going to talk about in this section before we talk about the central limit theorem, because that's specific to some average type of statistics. But Lévy's continuity theorem is a probability result. So it's very simple and very elegant. It says that the convergence in law xn to x is equivalent to the convergence in the characteristic function of xn to the characteristic function of x at pointwise convergence. And this is for any t in Rd. So by the way, to say that this is a constant vector in Rd, we also have xn and x in Rd. So they are d-dimensional random vectors. And previously, we didn't really emphasize the multi-dimensional thing. We just assume for simplicity d equals 1. So this is a random variable, and this becomes a constant. But the general result is for the d-dimensional, fixed dimensional random vector. Random vector is convergent to a random vector, and t is a constant vector. Okay, so characteristic function, we know it's a very useful function that describes the distribution. And you know what this is different from the definition of convergence in law, if you recall, is that in the definition, we use the CDF. We didn't use the characteristic function. And when we use the CDF to define it, we need to make an exception for the values or points where the CDF of x is not continuous at, right? So the definition is fxn x converge to fx x for Rx in the continuity set of fx. So we have to distinguish continuity points from the non-continuity point, discontinuity points for fx. But when we use the characteristic functions, it's different. So here the t is not really the x. What's the t? So I'm just going to define it here. So this is defined as the expectation of the exponential to the imaginary unit t transpose xn. This is the definition of the characteristic function. And I think some of you might have learned the moment generating function. So the difference is that in the moment generating function, we don't have the imaginary unit. Yeah, actually, we have a similar result using the moment generating function, but the characteristic function is more general, so we use it here in this class. And you see, for this expectation, if you write it out, what is it? It's actually this. Integral exponential it transpose x. This x is in the domain of xn's distribution. Say this x and d f xn x. So we can write it this way. And that's the, that's the definition of the characteristic function. And you can see that we can vary this t with this integration. X, the lowercase x will be gone, right? It will disappear after you do the integration, but t will stay. That's why the characteristic function is a function of t. And t is a constant vector in d dimensions. So you can do the inner product between t and any vector in the domain of your xn. Okay, so Lévy's continuity theorem is the key result we are going to talk about. But to be able to prove this result, right, why this will hold, we need a more basic theoretical result called the Helly-Bray theorem to start with. And so we will talk about that today. With that, then this proof will become more straightforward. And by the way, why is this result so important? The reason is that as long as we can prove the convergence in characteristic function, we can achieve the convergence in law. And also, this is an expectation, right? So basically, you can see that we can write this as expectation T transpose X. So we can actually write the characteristic function convergence as a special type of expected some functional transformation of xn to the expectation of the same functional transformation of x. So that's why you see the connection. There's a very clear connection between convergence in expectation and convergence in law. And furthermore, you see here, the original definition is essentially, maybe I should also say here, this is equivalent to expectation of the indicator function that xn is less or equal than x will converge to the expectation indicator x is less or equal than x, right? And also as a reminder, whenever we write expectation, we must bear in mind what distribution it is concerning or what random variable it is concerning. This is about xn and this is about x. Same here, this is about xn and this is about x. Okay, so coming back to the Helly-Bray theorem, it provides the foundation for proving Lévy's continuity theorem. And Helly-Bray theorem has 4 statements, and it says that the 4 statements are equivalent. The 4 statements are equivalent. Okay. So the first one, we call this A, is that xn converges in law to x. And the second statement is that expectation of a function g applied to xn converges to expectation of gx for all function g, all continuous function g, continuous, this is the key. G, actually I should say G here is a map from RD to R. So this RD is just to take account this that our xn is in RD, but the value is a real value function that vanishes outside a compact set. So what this says is that the support of G, where G has non-zero values, is compact, is a compact set in RD. And because RD is special, so in RD, a compact set is equivalent to a closed set. So for example, you can think about this as a closed cube in D dimension, Euclidean space. So this is statement B. So if we can show that for all such continuous and closed or compact support G function, we have this convergence in expectation after the G transformation, then we would have convergence in law. So then you can see that this is actually a more general condition or statement because we need to prove this for all such G. While in the Lévy's continuity theorem, we only concern about one function. That's this particular function. Okay, B. And C is more generous than B. It says that we have expectation Gxn converge to expectation of Gx for all continuous and bounded function G. So now the compact support is not required, but we require the function values to be bounded. Means that the function cannot take values as positive infinity or negative infinity. And finally, D. So D is the most general statement regarding the convergence in expectation. So I'll just make it simpler for you here. So it just generalizes the continuous function to measurable functions. And we require measurable bounded functions, but there's one more requirement. All measurable and bounded function G. And one more, such that we need the probability, I'll move here. We need the limit X random variable to be such that the probability that the random variable limit, random vector limit X is in the continuity set of G with probability 1. So that's what we need. So basically, you can see why we need that. It's just like, even though the function may not be continuous, but its discontinuity points do not matter. The reason is that X will not take any of the discontinuity points with a positive probability mass. So we don't care. So therefore, you see, it should be obvious to us that C is a special case of D and B is a special case of C. Okay, so obviously, if we have D already, D implies C, C implies B. But why do we keep B and C? Right, we're saying that all the 4 statements are equivalent. Why don't we just say A and D are equivalent and we're done? The reason, I think technically, the reason is that having B and C here will make the proof much easier. So basically, when we prove the equivalence between A and D, we will not directly prove that A implies D. Instead, we will prove A implies B, B implies C, C implies D, because that's more gradual. And then we're done. Okay, so the idea is that we are going to, so basically we can say that fundamentally, we just need to say that A and D are equivalent, but B and C are here to make the proof easier, to facilitate the proof. We will show that we will show that D can go to A, and A can go to B, and B can go to C, and finally C can go to D. So you see, we have a loop here, and with this, then we are done. So we can show they're all equivalent. So basically, A can go to D, and D can go to A, and we're done. Okay, so from D to A, it's actually quite straightforward. The reason is because A is defined as this, right? So as long as we can show this holds, we're done. And you see that this definition tells us the G function is the indicator function. As long as we can show this indicator function is a special case of D, we're done. So we can go from D to A. All right, so now let's do this, D to A. So to show that expectation indicator function xn lesser or equal than x converge to expectation indicator x lesser or equal than x for all x in the continuity set of fx. That's our goal. Okay, and to connect this to D, right? Our condition to start with, we define the G function as the indicator function. We define, so I'll just use this dot to denote the argument of G. We define the G as, oh, and also by the way, for the proof, I'm just going to assume D equals 1. Okay, so here the dimension. I'm going to assume D equals 1 to make the proof easier. Okay, so assume D equals 1 in the proof. And then we define G as the indicator function. I have the argument here, less or equal than X. That's my G. Okay, so then how do we do it? Then what's checking this condition statement D, right? We can make sure, of course, this indicator function, it is measurable, it is bounded because it has only two values, 0 and 1. What's its continuity set? The continuity set, if you think about it, is all the values except X, right? X itself is the discontinuity point. Before X, G has value 0. When it reaches X, G has value 1. So there's a jump there at X. Okay, so then G, CG here, okay, is just the set, or I would just say CG is just here, D is 1. So it's the real line except X. That's it. X is the discontinuity point. And then let's check if this holds. The probability that the limit is in the CG, right, is equal to the probability X is not equal to this X. And that's what? This probability is actually 1 because we already ruled out the discontinuity points of this fx. So which means that I should say that so basically this means this is, let me see if that's right. This is 0. Right, so I should say this. I should write this way. Yeah, so maybe this is easier to say. Instead of this straightforward way, I'll say the other event. So when X is not in the continuity set of G, it means that X takes the value X, the discontinuity point. And because this X, we know, is any value, any point that's in the continuity set of fx. It means that random variable X is continuous at this value. So therefore, it will not take it with probability non-zero. So it must be 0 probability for taking this value where the distribution is continuous at. So we're done. So then this probability is 0. And then the probability that X is in CG is 1. So we satisfy this requirement in condition in statement D. So we prove A, right? So basically the indicator as a special case of G is okay. Okay, so that's from D to A. So now we are left with proving A to B and B to C and C to D. So for those, you see, we are actually going to go from a more special case gradually to more general G. So first of all, let's think about how to do A to B. Okay, from A to B. So first of all, we need a compact set, right, for the function G. Let's say that we have a compact, say the compact support of G is C. We use C to denote that compact set. And because we are in this under the special case of one dimension, and this is R, right? So we can say that it's a closed interval. We just write it out as A to B to make it easier for us. So then G, the G function takes non-zero values only from A to B. And outside of A to B, G is 0. So, and it's continuous. Yeah, it's continuous on the compact set. So these continuous on the compact set, if you have taken analysis class, you will know that this implies this function is uniformly continuous on the set. So uniformly continuous versus continuous, maybe I can explain that a little bit. So basically, when we say that G is continuous, a continuous function, what it means is that for any small delta greater than, or maybe I'll just be consistent with notes. Okay, for any epsilon greater than 0, at a value in the domain of X, there exists a delta depending on X, such that we would have whenever X and Y is less than this delta X, we would have Fx minus Fy less than epsilon. So in other words, given a small epsilon in terms of the function value, neighborhood size, right? Given the value X, you can find the delta. And this delta is the neighborhood size in the domain. And for any Y that's in the epsilon X neighborhood of X, you can always make sure their function values are within epsilon. So this is the continuity or continuous function definition. But here, we're going stronger. When we say G is continuous and continuous on a compact set, so this will tell us G is what we call uniformly continuous. And it's stronger than just being continuous because now this neighborhood size delta in the domain can be independent of X. So we can find a common delta for all the X values. And this is defined as for any epsilon greater than 0, there exists a delta positive such that whenever you have X minus Y less than delta, you would have Fx minus Fy less than epsilon. So making that delta independent of X is very, very important. So I can tell you one particular example is that think about exponential function, Ex. So that Ex function is clearly continuous and it can go from negative infinity to positive infinity, but it's not uniformly continuous because you can imagine if you have X, let's see this. So if you can imagine, if you have a very large positive X on this side, if you want to find functional values that's actually, or I should say, yeah, move this side. If you want to find functional value difference that's epsilon, then the corresponding X difference will actually be larger and larger on this side and will be smaller and smaller on this side. So that neighborhood size delta will depend on where X is. But for the uniformly continuous function, you can find the delta independent of X. Oh, sorry. Yeah, that's right. It should be G. So coming back to what we need for B, we talk about this uniformly continuous G, right? That's implied by the continuity on a compact set. So this will give us some nice work to do. The reason is that given this compact set A and B, right? And let's say we start from some epsilon, we found delta, and given this delta, we can actually divide this interval into small pieces, and every piece will have length under delta. And with that, we can make sure, okay, on every small piece, the difference on the function value here, G, is very small. And so we can control that. And therefore, controlling that means we can actually approximate this G function on C by some step functions. And basically, it means that on every small interval, the approximate function would be flat. It's a constant. And therefore, that can connect us to indicator. Because the indicator function is flat. It's either 0 or it's 1. So basically, the idea is to approximate this G function using small pieces of step functions. And then we can go from what we have, statement A, from indicator function to step function, and from step function by approximation to B, to the function on B. So that's the whole idea for this proof. That's the intuition. All right, so I'll start writing what we have there. So to prove this, we fix epsilon first, the small epsilon, and find C1 to Cn, or C, maybe I should say this. Find this A, and A less than C1 to C less than C2 less than Cn less than B. So in that A to B interval, I find C1, C2 to Cn such that Ci minus Ci minus 1 is less than delta. So any two adjacent Ci's are close to each other, less than delta. And so this, I would say, I go from 2 to n. Or maybe I should, sorry, I should make it more straightforward, my bad. Yeah, I should say, I call this A as C0, and I call B as Cn plus 1. So I can make the notation more consistent. Okay, starting from C0, that's the A left boundary, to Cn plus 1, that's the right boundary B. So I want to make sure that they are within delta neighborhood of each other, and I go from 1 to n plus 1. Okay, we have this, and also I would like to specifically take the points in the domain of my X, right? So here the domain is just R. I want to make sure that these C1, C2 to Cn are where my random variable X, the limit, is continuous at. Okay. And I want to make sure this also happens. The reason I can achieve this is because we know a function can only have a finite number of discontinuity points. So therefore, I can avoid the discontinuity points where the X has positive point masses, and I just pick from those continuity points and also satisfy this neighborhood requirement. So with this, then, so this, with this means that, or I'm just saying this is equivalent to say Ci is in the continuity set of Fx. Okay. So with this, then we can have by the uniform continuity of this function G, right? So of this function G in statement B, we would have GCI minus GCI plus 1. Their difference is within epsilon. So we satisfy that. Okay, so then what's next? We are going to define an approximate function. We call that G tilde. And we define the G tilde x as the summation. Let's say that we have, right. So we have it as I go from 2 to n. And it is defined as G at Ci times the indicator function x. So this is the step function I was talking about. So when x falls on this small interval, we give it the value of G at the right boundary of that small interval. So then we are doing the approximation. So you see the approximation error only happens within each small interval. And we know that within each small interval, the approximation error is controlled under epsilon. So we actually control the approximation error. And also you can see that with this step function representation, we can actually rewrite it as the indicator function here, okay? As the indicator function here. So that means if we write it as this, we can reorganize the terms. And so we can write it as, I'm just writing it down here, summation I from 2 to n. And now we are going to say here, the constant here is not GCI, but we can write it as let me see here. I think it's J from, I think there's a typo in my notes and I'm going to correct that. Yes, I think this is actually J from 2 to I, GCJ. And this can be written as times the indicator function. Now it goes from negative infinity to Ci x. So in other words, I'm reorganizing this so that the indicator function is not on the small interval, but the left boundary goes to negative infinity to reach Ci. The reason we want to do this is because that can connect us to the CDF function here. I think there might be something wrong with the constant. Yeah, I'm going to erase it, but I'm just going to write it just as a, yeah, to make it simpler, I'll just write it as AI. So we know it's some constant here. Okay, so with this, then you see we're almost done. Because with the function in this form, you see that then when we write the expectation of G tilde xn, right? What we have is the summation I from 2 to n, AI, expectation enters here, and we actually have the fxn at CI. So did you see that? So we can actually write it this way, right? Because expectation of this indicator function and changing this to xn, that's actually my definition of fxn, the CDF. And we already know by statement A, this will converge to AI fx CI. We have the fx and CI converge to fx CI because CI is arbitrarily picked as a continuity point of fx. And this is what? This is expectation of G tilde x. So therefore, we can prove the convergence in expectation for G tilde. And what's left is just the difference in the expectation of Gxn and this expectation of G tilde xn. And on this side, the difference between the expectation of Gx and expectation of G tilde x. And we're done. So does it make sense? So the goal is to go from A to B. And because A is a special case of G function, this indicator function, we want to approximate this continuous with a compact set G by some step functions, and the step function can be connected to this indicator function. So we're done. All right, so finally, let's see, given that, what's left here is, okay, I think I'm going to erase this part. Right. Okay, so with this, so finally, if we want to do expectation of Gxn minus expectation of G of x, we want this to be very small, smaller than given the epsilon we start with. And this is what we need to prove statement B, right? This must be very small. And we can actually just write this. This is a common technique, right? We just minus the G tilde xn here and add it back. Right? And also we introduce the G tilde x, right? And add it back. So that's what we do. And then we use the inequality to write it as 3 absolute difference terms. This is the first term, and the second term, and the third term. All right, and so basically what we already have is that, so this can actually be controlled by this approximation error. So we have here. So essentially what we can say by the definition of G tilde, so we can actually show that the first term is less than epsilon, and the last term is also less than epsilon because of approximation error. And for the middle term, we know it's going to infinity. Oh, sorry, we know it's going to 0 because of this. So we can say that this is less than epsilon, this goes to 0 as n goes to infinity, and this is less than epsilon. And because we fix the epsilon to be any positive number to start with, we can shrink it down to 0, and then we can let this go down to 0. So that's it. So from A to B, it's just the first one. You can see how we do the approximation to go from this indicator function to this G function that's continuous on a compact set. Okay, so I think the idea is very similar when we go to B to C, from B to C and C to D. So I will try to quickly wrap up the proof from B to C. So you see here, the difference is that in C, we have the function G bounded, but it doesn't have a compact support. So the difficulty here is that we need this compact support for B so that we can have the uniformly continuous, and then we can have this C1 to Cn as the dividing points to get the small intervals, right? That's what we need for B. But for C, how can we go from a function in B to a function in C? So the idea is that because it's bounded, right? The function G is bounded. So what we want to do is that we want to find a large enough compact set for this function G, so that on that set, the function values are large. And outside the compact set, the function values are very small. So that's what we want. And then we can go use a function of type of a function that satisfies the condition in B to go to C. So I'll quickly talk about this and we'll see how we can do the construction. So from B to C, okay. Okay, so here now in under C, we have a function G, it's continuous, and we have Gx bounded by this upper bound A for all the x in Rd. And here we still talk about d equals 1. Okay, so what we want to do is that we want to consider, the limit of this limiting random variable x, because the key to consider is that we only talk about expectation, right? And expectation g of x is depending on mostly on where x has large probability masses. So if we can find a compact set where x has most of its probability mass, we're done. So we don't care outside of compact set because it have very small probability for x. So that would not affect expectation that much. Okay, so what we do is that we find the constant b such that what we have is the probability that x absolute value is larger or equal than b is very small. So now I'm just going to say it's under epsilon divided by 2a, and the a is actually the bound here. So we divide by 2a just to make sure in the final step we can have epsilon. We can have some cancellation of the a there. And still, this is starting from a fixed epsilon positive. We start from an epsilon, and we find this large enough b so that you can basically see that we try to have a compact set negative b to positive b that contains the most of the probability mass of x. As the compact set we want to work with. Okay, so we actually construct a function by modifying the function g in C, which is continuous and bounded. So we want to modify to be continuous and compact. So here, what we do is that we introduce this function hx. So we introduce it as this. So basically, we want it to be equal to 1. So if x is within this interval. So we keep as 1. And we make it 0 if x is greater or equal than absolute value b plus 1. So in other words, to draw the function, it's like this. From negative b to positive b, it stays at 1. And then it will go down to 0 here and go down to 0 here. So you see, that's the function we introduce. And what's the compact set of this h function? So I should modify this. It's actually from negative b minus 1 to b plus 1. So that's the compact set. And then we are going to use gx times hx. You know, this function will satisfies the condition in B. It's a continuous with a compact set function. And to use it to approximate the function gx in C. So this is just to ensure that, okay, they are identical. You see, they're identical in this interval, negative b to positive b. They're identical. And they start to differentiate in this part and this part. And outside, we have this function vanishes at 0, but this function, even though it may not be 0, however, outside from here to here, my random variable x has very small probability. So it can be negligible when we calculate expectation. So that's the idea. And then we can go from B to C just because the expectation. So still, the idea is that we are going to show expectation of gxn, hxn. This is a function that satisfies B, will converge to E expectation of gx, hx. From B, we will have that. And then we are going to show that, yeah, so the expectation of gxn, hxn minus the expectation of gxn will show this term is small. And also expectation of gx, hx minus expectation of g of x. This term, they're both small. We are going to reduce them to our epsilon. And then the argument will be similar to the proof from A to B. So yeah, so again, this is an approximation. We try to use a function of type B to approximate any function of type C. And then finally, from C to D is another approximation. We're going to approximate such measurable and bounded function by a continuous and bounded function. So I think I can stop here. And so to wrap up this part, because I think the details is something you can read in the notes. And the idea is that we want to, so the key point is that we want to show the equivalence between A and D, right? And then with this equivalence, this continuity theorem would become straightforward because with D, we can prove this part, the convergence in the characteristic function, and that will give us the convergence in law. Okay, so I think we will stop here for today. And starting in our next lecture, next Monday, I'm going to maybe do a quick recap of this Helly-Bray, and then we will start talking about this continuity theorem. All right. So thank you all. Stop the recording.